Were you ever out in the great alone when the moon was awful clear, and the icy mountains hemmed you in with a silence you most could hear? With only the howl of the timber wolf as you camped there in the cold, a half-dead thing in a stark, dead world, clean mad for the muck called gold. While high overhead, green, yellow, and red, the north lights swept in bars. Then you've a hunch what the music meant. Hunger, night, and the stars.
The Aurora, and the words of Robert Service describing life at the extremes in the Yukon Gold Rush. You have to be very lucky to see the Aurora in Britain, even here in the north of Scotland, because it's essentially a phenomenon of the polar regions. Your best chance is when there are lots of sunspots, when the sun's at its most active, and that seems almost perverse. A polar phenomenon, usually seen at night, yet linked to the sun. The connection is long and fairly tortuous, but it involves both magnetic fields and plasmas. And it's with plasmas that we'll start our story. Most of the universe is a plasma. Plasma streams out from the sun. The upper atmosphere of the Earth contains a plasma. But where's the plasma here? We normally see matter in just 3 states: solid, liquid, gas. For example, ice. Well, there's no shortage of that in this environment. Water, likewise. Steam, well, I cheated and brought that with me. Why no plasma? Well, the simple answer is that the state of a substance depends on its temperature. Heating it up changes that state. At a basic level, all matter is composed of protons, neutrons, and electrons. Think about a typical, very cold solid. Each molecule in the solid contains the same number of electrons and protons. So everyday matter contains vast amounts of electrical charge, but shows little direct sign of it. Now start to heat the solid. The molecules begin to wobble more and more energetically. Given enough energy, the structure breaks down and becomes a liquid. And then with more energy still, as the density falls, it turns into a gas. As the temperature rises further, the molecules themselves break up into atoms, and when the temperature is high enough, the electrically neutral atoms split up into separate ions and electrons. The ions, here shown in red, are positively charged, and the electrons, shown blue, are negatively charged. This is the plasma state, a sea of intermingled charged particles. And like a sea, it can carry waves. Energy put into the plasma will ripple through it. We can't fully understand the ocean without understanding the motion of the waves. And similarly, to understand a plasma, we have to understand the way it moves. We'll come back to this point later.
Well, that in outline is the theory of how plasmas are produced. Does it work? Well, it certainly does. Here we've got a partial plasma of oxygen. And we're creating that plasma inside a vacuum vessel at the Culham laboratories. Culham is the centre for plasma research in the UK. How do we go about creating that plasma? Well, the first essential component is the vacuum vessel itself. Because if you want to create a plasma, you have to create an empty space into which the plasma can be placed. And once you've got that space, you introduce a gas. In this case, we can do it using these electrically controlled valves. So with the gas in the vessel, we then heat it up. And in this case, we do it electrically using a power source beneath the bench. And it obviously works, because here we have a nice oxygen plasma. And I'd like you to notice the colour. It's a light green, with perhaps just a tinge of purple underneath. and the colour is characteristic of the plasma. Oxygen plasmas are light green. If we change the gas from oxygen to nitrogen, the colour changes from light green to pink. Different parent gas, a different colour. Now, green and pink are the dominant colours in the aurora, and nitrogen and oxygen are the dominant gases in the atmosphere. And that's highly suggestive about how the light in the aurora is produced. And it's the production of light that I want to talk about now. I made quite a point earlier on about saying a partial plasma, because the existence of atoms as well as plasma is important for the production of the light.
Paradoxically, perhaps, true plasmas are dark, an observation that is easy to demonstrate with one of the larger experiments here at Culham. This is a machine called START. It may look a bit complex, but in fact, in essence, the machine is very simple. Its function is to create a hydrogen plasma in a ring around a central column. The plasma only exists for a brief moment, barely 1/20th of a second, but during that time it can be observed through portholes in the wall. Here you're looking through the plasma from the side. From this position, the plasma appears to have a D-shaped cross-section on both sides of the central column. It's in the centre of each D that the temperature is highest, and so that's where the hydrogen gas is most completely converted into a plasma. Comparatively little light comes from these regions. Nearer its edge, the plasma particles collide with the hydrogen atoms of the parent gas and lose energy. They cool. But at the same time, they excite these atoms. The energy they transfer is subsequently radiated as light, and that carries the characteristic colour signature of the atoms involved. For hydrogen, this is red. So in this machine, the brightest part of the plasma is at its surface, where it meets and loses energy to the surrounding hydrogen atoms.
Careful measurements confirm that the light from the aurora is indeed from the nitrogen and oxygen in the atmosphere, and that's consistent with the energy coming from collisions with plasma particles. It is the atmosphere that is glowing. In fact, the colours of the aurora captured in this photograph from the Space Shuttle have been analysed as being mostly due to plasma collisions with oxygen, and you can just make out the green and purple glows associated with oxygen plasmas. We seem to be on the right track, but we haven't explained how this particular plasma is produced, nor why the aurora only appears high up in the atmosphere and in a ring round the poles, a fact that's borne out by these images of auroral activity tracked by the Dynamics Explorer satellite. In fact, all the explanations begin with the Sun. Remember, the Sun's corona is a plasma. The energy is provided by nuclear reactions in the Sun's interior, and massive gravitational forces hold the corona to the Sun's surface. In spite of these forces, the corona continually escapes as a stream of charged particles flowing at hundreds of kilometres per second away from the Sun into space. This stream of particles is known as the solar wind, and as you will see, it plays a significant part in the story of the aurora.
Here at Culham, the central aim is to mimic the Sun, to create a plasma that's hot enough and dense enough to allow fusion reactions to take place. And that means confining a plasma at a temperature of millions of degrees. That's very hot and very difficult. Now, the scientists here can't use the same trick as the Sun does. They can't simply use gravity to hold the plasma together. There simply isn't enough mass. And they can't rely on the walls of the vacuum vessel, because the plasma will interact with the walls, it'll simply melt them. Instead, they have to find a way of pulling the plasma away from the wall into the vacuum. And to do that, they use magnetic fields. Now, the interaction between magnetic fields and plasmas is crucial to start and it's crucial to our story. We'll spend a little time on it. But in start, the geometry of the magnetic fields is rather complicated. This is one of the conductors which carries the current which produces the magnetic field inside the vacuum vessel. But there are several of them, and the magnetic field geometry is complicated. And so we'll use a simpler arrangement than start to look at the interactions between plasmas and magnetic fields. This is a demonstration apparatus used by Cullen. In the apparatus, there's a glass tube within which is sealed a small amount of gas. In the centre of the tube, there's a coil, and that coil can be used to heat the gas and turn it into a plasma, well, in fact, a partial plasma. The gas happens to be neon, and so the plasma turns out to be orange. Orange is the characteristic colour for neon. We're interested in the interaction between the plasma and the fields. And you can already see, if you look closely, that there is an interaction. At the far end of the tube, there's a small disc magnet, and that's shaping the plasma in this region. If I put the second one in at the other end, it too shapes the plasma. Clearly, there's an interaction between the fields and the plasma. Now, we're interested in the microscopic details of that interaction, and we'll start off with the simplest possible case, without any magnetic field present.
The ions and electrons move in random directions. Let's just focus on one of the ions and turn on a magnetic field which is uniform in the small region we're looking at. The ion spirals along the field. An electron behaves in much the same way, but it twists in the opposite sense. Looking along the field, the ion would appear to be following a circular path, guided by the Lorentz force. There's no magnetic force in the direction of the field, so the axial speed is constant. The path is helical. Now look at what happens as the magnetic field becomes non-uniform towards the end of the tube. There is now a component of the field perpendicular to the axis, which gives rise to a force on the particle back along the axis. This compresses the helix and eventually the progress of the particle. The non-uniform field acts like a magnetic mirror, reflecting the ion. Put two such mirrors together, and you create a magnetic bottle in which the particles bounce back and forth between the two ends, all the time spiralling round the field lines. In reality, magnetic bottles aren't perfect. That's certainly the case here, where some of the particles have just the right trajectory to squeeze out of the ends.
There's also a form of magnetic bottle that can confine plasma near the Earth. To understand why, we need to look more closely at the Earth's magnetic field. Close to the Earth, this field looks very like the field of a bar magnet and can act as a magnetic bottle for charged particles such as ions or electrons. In this case, the magnetic bottle has a strange shape, but the principles are the same. Let's consider electrons this time. They spiral along the magnetic field lines and are reflected near the poles where the field becomes stronger. The round trip from pole to pole takes a typical electron just a few seconds. At relatively low altitudes, this magnetic bottle contains nitrogen ions, oxygen ions and electrons, created by ultraviolet light falling on the atmosphere. But at higher altitudes, the shape of the field becomes distorted. Further out from the Earth, the solar wind, the stream of charged particles flowing out from the Sun, shapes the Earth's field, compressing it on the side nearer the Sun and drawing it out into an elongated tail on the downwind side. By mechanisms that are very poorly understood, some of the plasma becomes trapped in a now very distorted magnetic bottle. The trapped plasma forms huge plasma sheets. Now we are quite close to an explanation of the aurora. In the discharge tube, some of the plasma leaked out of the ends of the bottle. Here a similar thing happens. Some of this plasma leaks out of the ends of the Earth's magnetic bottle near the poles and encounters the Earth's atmosphere, where it causes the oxygen and nitrogen atoms to glow. The total energy produced each second in a strong aurora is enormous, equivalent to the output of about 20 large power stations. But research into the aurora has identified a problem with that energy. The energy of the incoming plasma has been measured directly, and it's clear that some of the electrons involved in creating the aurora have quadrupled their kinetic energy as they travel down towards the atmosphere. So what's accelerated them? That question has occupied space plasma physicists for decades. They'd all agree about some things. For example, we're looking for an acceleration in the direction of the magnetic field. But magnetic fields accelerate particles perpendicular to themselves. So without a doubt, the Earth's magnetic field can't provide the required acceleration. What about electric fields? Well, that's where the controversy starts. One of the people deeply involved in that controversy is Duncan Bryant, who has worked on the aurora for many years at the Rutherford Appleton Laboratory, just down the road from Culham. But we've both come here to a ski resort because the activities on the slopes will help us to picture the physics of the problem. For example, here you can see what's been the conventional view. A static field accelerates the particles downwards. There's a potential difference between high and low altitudes. As the electrons move down the magnetic field lines, they lose electrical potential energy and gain kinetic energy, in much the same way that the skiers gain their kinetic energy at the expense of gravitational potential energy. So the conventional view is of a static electric field accelerating the particles downwards. But, Duncan, I know you have an objection to that explanation.
Yes, but the objection is not to do with the analogy. In fact, skiing makes an excellent analogy with which to demonstrate the problem that some of us have with the static field model. The problem is that it leaves out a vital element, the ski lift. The function of the ski lift, of course, is to provide the potential energy. At the moment, the static field theory includes no equivalent of the ski lift. There's no mechanism by which the electrons are given their initial potential energy. And what's more, there's no direct evidence for the existence of the potential hill itself. So my colleagues and I find we can't subscribe to such a theory. But how might the electrons be accelerated? Consider instead a related but crucially different sporting analogy, surfing. This could be thought of as skiing on moving hills. Surfers know that they have to catch the wave. If they match their speed to that of the wave, they're pushed forward and draw energy from the wave. If the speeds don't match, there's no acceleration. So waves can provide selective or resonant acceleration. The question we posed was, could something similar be operating in the aurora? Remember, we're looking for a wave to drive electrons along the magnetic field lines. Well, there's a type of wave called a lower hybrid wave, which is a bit like a sound wave, except that the compressions and rarefactions aren't in density, but in electric charge. Lower hybrid waves travel almost but not quite at right angles to the magnetic field, at the slow speed of the ions. But due to the angle of incidence, the resulting speed along the magnetic field lines is much faster and gives exactly the resonant matching conditions we need for electrons. I believe these waves may well be responsible for accelerating the electrons which produce the aurora. There are still things to be clarified. For example, how are the waves generated? And are they strong enough? The only way to find out is with more measurement.
Yes, clearly the debate's going to continue. And the reason it's already gone on for so long is that plasmas are very complicated. They move in electric and magnetic fields. Their constituent charged particles create electric fields, and then when they move they create magnetic fields. They respond to the fields that they themselves have created, and so on. Because of this complexity, we still don't have a neat and tidy explanation of the aurora. And exactly the same problems occur in trying to understand other plasma systems. In the Sun, the magnetic fields are large, and the plasma is far more dense, so its writhings are intense and dramatic, as illustrated by this solar flare, where the plasma arches along field lines above the visible surface of the Sun.
The interactions of plasma and fields are researched with great urgency here at Culham. Let's come back to the START machine. The objective of the START experiment is to improve methods of controlling plasmas. Remember, at the core of START is a magnetic bottle in the shape of a torus. This eliminates the problem of leakage from the ends, since a torus has no ends. But leakage is not the only difficulty to overcome in confining plasmas. Internally generated instabilities tend to grow uncontrollably and catastrophically. This can be seen very clearly in this view of a toroidal plasma in another machine. The plasma, hottest in its dark centre, begins to writhe in its confining magnetic field until eventually it escapes and hits the wall of the vacuum vessel in which it's formed, vaporizing it immediately. In the process, the plasma is contaminated by the vaporized wall and cools. To control and confine a plasma is a task that's been compared to holding a jelly in a string bag. START may offer one promising avenue towards this goal, for its plasma seems remarkably free of violent instabilities. But it isn't the only avenue that's being explored. There are other machines, other experiments. The largest in the UK is JET, the Joint European Torus. What's hoped for is that all the data from all the machines will come together and will guide the design of future plasma fusion installations, leading eventually to a useful power source, mimicking the Sun. That's just about the end of our plasma story. At the heart of it is a basic law of physics, the Lorentz force law, which governs the way charged particles respond to electric and magnetic fields. It's a remarkably simple law, and yet it's able to throw light on phenomena as diverse and as complex as the confinement of plasmas, the aurora, and even the Sun.